Perfect. Okie dokie, okie dokie. So, welcome in, guys. What week is it? Is it week 3, week 4? It's week 3. Yeah. Week 3. Hope you guys have had a good start of the quarter so far. I've been tired, but you know, that's part of the fun. So today we're doing convolutional neural networks. Convolutional neural networks, as you will quickly come to find from what we're covering today, are really, really good at analyzing images, which is something that we noticed they aren't very good at during week 1 when we covered the perceptron. If you guys don't remember or you weren't there, what we did in the perceptron was trying to predict whether or not an image is of a cat or of a dog, and we ended up getting like pretty poor accuracy. I think around 60% of the time we got it right, which is just slightly better than guessing for something that's 2 options, which is pretty garbage. So what we're going to do is try and improve on that today by changing how we analyze images. So as a brief recap to neural networks are a system of interconnected nodes in neurons. So more or less every single one of these points on this graph is a neuron within this neural network, and every single one of those neurons does this operation at every step. The node's value is calculated using the previous layer's values. So if, let's say we start here, this is our input, each of these has a connection to every node in the next layer, and we use those to calculate the output, so the prediction from each of these neurons, which then feeds forward into the next layer. So predictions based off of predictions based off predictions till you have a final prediction, which is your output. And all of those values, so these weights here, so omegas, and the B here, which is the bias, all train and can be learned over time to improve your prediction. And this is done through a process known as gradient descent, which we went into a decent bit of detail last week. But more or less, the general concept is you try and improve your prediction by being wrong and adjusting your weights over time. Any questions on this very brief recap that we're going through? Dope. All right, so, oh, yeah. How do you mean? For which specific? Yeah. Okay, so do you see this upper diagram here? Okay, excellent. So the node here, another word for the neuron here, this is the main unit of calculation of the network. So each one of these points here on this graph represents one of these. So the input to it, just like x1, x2 to xn, is the vector of input values. So for example, how tall someone is, how much they weigh, how much money they make, what their shoe size is, etc. We use that as input. Then we adjust those values with some weight value. So each input gets its own unique weight, which can be learned over time. So that allows you to modify it in some way, make more values more or less important over time, which you learn by just predicting it. And then we add in some sort of bias value, which is also something we can learn, and sum them all together. So the sum of this is basically our basis. This is our prediction value that we're going to be doing our analysis based on. And we pass that value into our activation function, which is more or less just a way for us to influence what the output looks like. So if we want to, for example, bound it between 0 and 1, we might use something called sigmoid, which is very, very common. It's a good way to do statistical prediction. Or something like ReLU, which is just if it's less than 0, it's 0. If it's greater than 0, it's 0. And so we pass it through that function, and that is now our finalized output, which we then use as the input to the next. Does that answer your question? Okay, perfect. So that's, again, the basis of neural networks. We can talk more about this at length, but the focus today is processing images. So quickly, what's the problem with traditional neural networks? I've mentioned it a couple times today, but can someone quickly spit it back out? What is the problem that we've noticed with traditional neural networks? Or one of the problems, because there's yeah. Yeah. I mean, that's a data related question, but 100%, yes, over here. Yeah. A lot of input is definitely processor intensive, 100%. More specifically, this isn't something I directly talk about, but I wanted to see if anyone could stumble into it. The problem with this is that inputs aren't considered related. So let me explain what I mean by this. Consider this broken up image of a cat. It's just divided into 4 for ease of our understanding. We have its left ear here, its right ear here, its face and neck, and its face here, right? So there's some relationship between them. So imagine that each of these are like different properties within a network. If we want to have spatial relationships between these, like it really matters that this ear is attached to this ear, and we know that they're together, then doing something like this doesn't make a lot of sense, where now this is more related to this, and this is more related to this. And neural networks can't do this by default. There is not something that the vanilla network can do. Like we could order these in whatever order we want, and the network won't be able to tell the difference between them. So if, for example, we're trying to process an image at a smaller resolution, this is just like a quarter of an image, but if we went by like pixels, right? So like we want to see these pixels right here, like on the edge of the ear, those we want to be related because they're part of the same specific structure. But if we try and pass it into a normal neural network, it has no way of knowing that those pieces are related whatsoever, which really isn't useful for our cases. So we need to improve our system, which means, there we go. Oh, that took a while. Let's go this way. Perfect. So what we need is a convolutional neural network. The convolutional neural network is a system that was designed specifically with the focus of processing images. More or less, what you do is you use filters, which we'll talk a little bit more about in a second, to process the image and look for features. So the values of these filters can be learned, which we'll again talk about and do some examples so you guys can get a better understanding in general of what that looks like. And there's multiple types of layers within a convolutional neural network. There's convolutional layers, which again, more detail in a moment, and pooling layers, which we'll also talk about. And then all of these results are then passed into a feed-forward neural network. So what we did last week, the base artificial neural network is what you pass the data into after this in order to do actual prediction. This is just to process the image in a way that makes it understandable. Any questions so far? Because this is confusing. Yeah. Yep. So let me go to the next slide. Your answer will be question. Question will be answered. So let's look at the example of like processing numbers, for example. Let's see here that we have like a 1. You can see here in this image here, all of the edges, all the filters can detect this. So like if we were able to pause the skip, we can't really easily, but imagine we can. We'd be able to see the ways that these filters can detect the edges of the shapes. So what we're doing more or less is we're passing small boxes over the field of the image and just more or less doing, we're just doing a summation. So every value within the filter, every pixel that it's looking at has some sort of value. We'll do an example on the board in a second if you want a consideration of what that might look like. Where then we just multiply each value of the pixel with each value of the filter and sum them all together. And that is the value within the next convolutional layer. And if you want more convolution, so what this does is it relates pixels to each other and gives you patterns. If you want an additional convolutional layer, you relate patterns to patterns. And you basically keep stacking this reference onto itself. So what ends up happening is you can pass in like an image here and pass over 6 filters and get out 6 augmented smaller versions of that original image, which contains specific information about the patterns within the image. And this is very useful for predicting because now you know the relationship between the pixel here and the pixel here, and the pixel here and the pixel here, instead of just having them strung together in a way that you don't fully comprehend with a standard network. So if we do that again, we're able to make relationships within those patterns, growing our field of view and learning more information about the picture every single time we do so. And again until it's more or less incomprehensible noise to us, but it's very, very useful for predicting for the machine. So here we can see it ends up having like a 99.95% confidence predicting the 4 and the 1, etc. That's a lot of information, but do you guys want to quickly do an example on the board so we understand what we're doing? Excellent. So imagine this very, very simple image. For example, in this case, what we're doing, actually, hold the mic for a second. What we're doing, imagine we have this simple image here. It's 4 pixels by 4 pixels, and every value is 0 or 1. It's a 1-bit image. So we're working in the space of black and white. What we're trying to do in terms of processing this is filtering with this pattern here. So in the top left, it's 1, top right is -1, bottom left is -1, and bottom right is 1. So we're looking for diagonal patterns. If it's strongly diagonal from the top left to the bottom right, then we're going to have a value, we're going to multiply all those values by 1. If it's by top right to bottom left, it's going to be negative. So let's pass this filter over this original image. So going on this square here, can anyone tell me what the output value should be? So what we're going to do is multiply all of the values in here with the respective value in this coordinate. So 1 times 1, 0 times -1, 0 times -1, 1 times 1, what should we get? Yeah. We're going to be summing them together. Don't forget it's just that transformation. Perfect. 2. Okay. What about this one? What are we going to get? Yep, -1. Perfect. Keep going. What's the next one? Yeah, 0. Okay. This one, I know it's going to get a little bit incomprehensible, but this is like a negative diagonal. What are we going to get there? -2. Thank you. Anyone else can also jump in. What about this one here in the middle? 2. Perfect. Over here now. Yeah, -1. Perfect. What about this one in the bottom left? 1. Next. 0. And the final one. Perfect. Okay. So that's a simple convolution over this image. We can do the same thing with a different filter. So for example, if we wanted to find whether or not there's a vertical line in an image, it's going to go to the next one. We can look at something like the bottom left here. So in this case, where we have a image that is just this square. So we have one that is very, very positive and one that's 0. This is our original image. So we want to pass over this filter here, which is just checking for vertical lines. So if there's values here, multiplied by 1. If there's here 0 and here -1. And the end result is that we find a middle band in the image where there's a border. So here, the filter of 3 is going to be passing over from here to here and from here to here. And so the end result is going to be this patch of positive values in the middle and nowhere else. Perfect. Is that clear for everyone? Just based off of this kind of simple example? This is literally all convolutions. This is the convolution operation. And this is how it works. And that's what makes these so interesting, because you're able to more or less condense the information of the network down into a more information dense form. Even if it makes less sense to us because it's more compressed, it's more information rich for the model to process. And that makes it a much better predictor. Yeah. They're learned. So it starts off as randomly initialized values. And they're doing the exact same process as a normal feed-forward network. You back propagate through, adjust the losses, and get out a value that's more precise. You can try and like force it to come up with specific types of patterns by limiting the amount of filters that you provide it, which we'll look at later today, actually. But generally, it doesn't really make a difference. Oftentimes, the stronger predictor is going to have more filters. Okay, any questions? Okay, we can work with that. Nice. So here's another example. I don't know if you guys were able to find us at Cornucopia, and I have more of these if you guys want them. They're in my bag. But we gave out stickers, and I'm really proud of these because I made them. The process that I started out with was making this original banana slug sticker. It's really awesome. And then what I did is I passed over this sort of convolution here. This is actually not exactly what I did. I passed over one that's 5 by 5, but that really wouldn't look very nice in the slides. So I passed over this filter over this, each pixel going with a stride of 1. So we're moving over 1 square at a time, every single step, moving over 1 pixel at a time. And the operation that ended up was doing something like this. This is more stylized, but generally is the idea. Obviously, the letters wouldn't appear out of nowhere. I'm not that magical with doing code. And the borders are very, very clean because this is something that I end up making myself off of the code. But this is more or less the convolution that came out from this by passing and looking for horizontal numbers. Or horizontal patterns, yeah. I actually don't think I padded the image on this. I'm pretty sure it's just like a little bit smaller by like 3 pixels. Yeah, we'll get to padding in a second. But yeah, so what we did basically, or what I did, is I passed a filter over this image and just extracted the values in terms of contrast. So wherever it was really positive, I think I gave it yellow, and where it was negative, I gave it blue. And that allowed us to find horizontal strips where it's roughly the spectrum from blue to yellow in a way that reflects your club colors. It's pretty neat. If you guys want stickers, I have them in my bag. You can take as many as you want. I still have like a few. So, all right, perfect. Any questions? Nice. All right. So first bit that we need to understand a convolutional network in terms of like how it does stuff is looking at a convolutional layer. So this is what we've done already. On the board there is our example where we did the actual convolutional process. And there's a few things that make this process a bit easier. So I don't know if you guys noticed, but when we passed over this 2x2 filter, the image shrank by 1 pixel, which a lot of the times isn't something that you really want if you want to keep the image the same dimensionality. So like you don't want it to shrink from 250 pixels to 248 pixels. You can add padding on the edges, and that'll make it retain the same shape, which is this blue box here. Alternatively, if you want it to shrink a lot more or represent more of the image per step, you can add something called stride, which is basically just changing the amount of space that you walk each step. So here, if you look at this GIF, we start in the top left, we take 2 pixels over to the right, and we end up shrinking a 5x5 image to a 2x2 because of the size of our kernel. Okay. Any questions so far? Feeling good? Spicy? Swanky? Nice. All right, and this is just a quick example showing a bunch of different combinations, so where there's no padding and no stride, padding and stride, etc., and how it relates to a typical image. You guys can look at this later. It's not super important for our purposes. I just wanted to include this as an example for you guys to check out later. Okay, the next thing that's important is a pooling layer. Pooling layers are a way to condense the size of the network. So what we're going to be doing in these is shrinking the size of an image with a specified operation. Typically, it divides it by 2. So what we're going to start out with is like this. I pressed the wrong thing. Sorry. There we go. Perfect. This 4x4 image over here in the bottom left. We'll just put this down. Use the arrow keys. This 4x4 image in the bottom left. We're going to pass over it what's called a max pool with a 2x2 filter and a stride of 2. So we're going to take a step of 2 pixels every time, and our filter's too big. So for a max pool, if you guys couldn't tell from the name, we're going to take the maximum value from within each filter. In this case, 2, 2, 9, and 4, 9 is the greatest. 7, 3, 6, 1, 7 is the greatest. 8, 5, 3, 1, 8, and then 2, 4, 2, 6, we're going to take 6. And the max pool is going to give us the maximum value. Average pool is doing the same, but taking the average within. So instead of like 9 in the top left one, that would be 8 plus 9 divided by 4, call it like 4.25. And you do that for every single one, you keep going down. So it's different purposes, different steps. But generally what it does is pretty, and it's very useful. Again, this is for condensing information. So if, for example, you want your image to shrink and lose out a bunch of noise, you can do something like this, and it'll retain the more important features or the general shape of the data if you take an average. Think of it like downscaling an image. Okay, cool. Any questions? Because this is generally what you do. And those are the 2 options for convolutional network. You can either filter it in some way, or you can shrink it. And it's a way to just increase the density. Yeah. Ooh, okay. So if you're interested in the extrema, right? So the thing that really, really defines that region. For example, if you're looking for bright spots in an image, you're going to want to do a max pool, because what you're looking at is the things that are most present. So if, for example, this image represents, I don't know, like the incidence of vertical lines in the original image, like these are the really big values are going to be where those lines are very, very prominent. And so if you take this on a much bigger image, on a much bigger scale, what can end up happening is you scale it down a lot and you keep the general trend of where the brighter spots are. So it allows you to condense the information in a way that you can really focus on the maximal output. Average pooling is also very useful because it allows you to keep the shape of the data, but this way allows you to encourage larger values. There's use cases for both. Yeah. Not necessarily. The filters can have fractional values. There's no inherent reason why it should get bigger. It could do that, but the odds of that actually ever causing a problem are very slim. The main thing that you need to do with this is like not go down to 1 pixel, because there is some amount of information that is lost every step that you do this. Like, yes, it becomes easier for the network to process, but if you take a 2048 by 2048 image and condense it down to 1 pixel, the model's not really going to know anything about that. It's just going to look like a single pixel, and you lose a lot of information when you do that. So there is some sort of balancing act that you really just feel by changing the parameters of the network. But that's the general thing. So don't shrink it too much. Don't make it too complicated. Yeah. You can choose the amount of filters each step. Oh, yeah. It's like it's a feel around and find it out process. You need to do a lot of it. Yeah. Yep. Just instead of doing like a different operation where you're like adjusting the data, you're just literally taking this input. Exactly. Perfect. How are we feeling? Thumbs up, sideways down. Nice. Okay. It's good stuff. Perfect. So the last thing that we need to do before we pass it into a feed-forward network is called flattening. Flattening is used because feed-forward neural networks are lame. I say this with a bit of exaggeration. They're very, very useful for a lot of different things and the basis for a lot of modern computing, but they aren't taking data that isn't one-dimensional. So images, if you guys know or don't know, are three-dimensional. There's the width, the height, and the amount of color channels. So typically red, blue, or green, or like just like one color channel for looking grayscale. Regardless, it's like a 2 or 3D thing. If it's grayscale, it's 2D. If it's a color, then it's 3 dimensional. There's some amount of depth because you're working with the red, the green, and blue, or like cyan, magenta, yellow, and I don't know what the K is. But you guys understand. So more or less what flattening does is you converted the 3D or 2D data into a 1D array. And this makes it processable by a normal feed forward neural network. And this allows you to take the image transformations and turn them into actual predictions, which is why this is arguably the most important step of making a convolutional neural network useful, because it allows you to make the data predictable. But yeah, that more or less covers the actual fundamentals of what a convolutional neural network is. So this is an overview of how a completed convolutional neural network works. Let's go with predicting numbers again as an example. This is a very common thing people like to teach you with. So we start out with like a 2 here. What we do is we pass a 5x5 kernel with valid padding, which basically just means we have no padding to the thing. It's dumb. And we end up with, how many there are here? It doesn't really matter. We end up with n filters passed over this original image that are now 24 by 24. Then we're going to do max pooling, which you can see shrinks it from a 24 by 24 to a 12 by 12 because we're taking the maximum value within a filter of 2 by 2. So the image size gets half. Then what we're going to do is we're going to do another 5x5 convolution with valid padding. So we're not going to add anything on the edges. This just means that it's within the bounds. It's going to shrink by 4 pixels again. So it's now 8 by 8 with n squared channels, I guess. And we're going to do it for max pooling and end up with a 4 by 4 image, which we then flatten and pass into a neural network to predict the value of. So assuming it works, it'll predict the value of 2. Yeah. 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 Yep. So more or less flattening. Here, we could work with this image as an example. If we were to flatten our convolved image, what we would do is string them together going in row major order. So top left to bottom right, like 2, -1, 0, -2, 2, -1, 1, 0, 0. And then you would do that for each channel strung together. So you go RGB, and then you do that for the next image. Yeah. It's convention. Because typically data is stored in row major order. You end up just doing it that way. So it really makes a difference. If you want to be weird and use a language that does things in column major order and re-implement it, be my guest. But everyone uses row major order, so it's always done in row major order. Yeah. Yep. Yeah, I think that's what the activation is here. So basically it's taking this flattened bit in as the input layer for this network, and then it's layer 1, layer 2. And I guess there's dropout from N3 to the output. Yeah, I'm fairly certain that's what this diagram means. Okay, perfect. Any other questions? Feeling good? Yep. Each filter. Yeah. So as an example, if we had this image in 3 channels, then what we're going to do is this would be n times 3. So we have n channels, so it's 3n. For each color channel, we have its own filter. I think it's just like 2. Yeah. Yep. But it's super dope and it's really, really useful. Now for a quick little glance at applications that we have for this stuff, because we have a lot of code to go through actually. This is very commonly used in facial detection. So what we're going to be doing today is actually an example of this. We're going to be predicting if people are happy or sad. So a lot of the time where models tend to look for is like patterns, spaces, specific angles, specific shapes, whatever. It learns this intuitively and over time, and allows you to predict what the emotion of the person is. Doing a simplified version, of course, because otherwise you need a lot of data. This is one very common example. So literally just detecting where people's faces are as a rudimentary technology, or just like this type of sentiment analysis. Another one is object detection and semantic segmentation, which is an extension of facial detection. So here we can classify this using convolutional neural network, that it's a cat. We love cats, very cute. Here we can say where the cat is by drawing a bounding box. You can see this a lot of the time if you look at mock-ups of what self-driving cars end up seeing. There's a lot of the times like boxes around the things that they see, and it says like what that thing is, like a stoplight, a trash can, a person, maybe both. So here it's drawing the box around the cat and where it thinks it is, which is very useful. Here it can detect multiple objects. This is like the advanced version of self-driving cars do. So we can see that there's cats in red, dogs in blue, and the duck in green. And here, this is called semantic segmentation, which is very complicated, and I'm not going to get into in this talk because we don't need that. More or less, it allows it to specifically draw the outline of where that object is by doing some complicated little bit of analysis. Yeah. It's not that simple. If it were that simple, you would have solved a lot of people's time and problems. But semantic segmentation for a long time was an unsolved problem. Being able to accurately describe where things are quickly and accurately is very, very difficult. If you guys are familiar with something like chroma keying, that is a common solution to it. It allows you to like film something on a green screen and then cut the person out automatically by keying out the green color. So that was like, just, oh, here's a color that we can very easily filter out, use this. But doing this automatically, we're able to detect the thing in an actual scene is a bit more complicated. So we can't actually do a very easy edge detection. Yeah, but that more or less covers it for us. Oh, right, there's one last thing. You can also use audio classification. So this is an example of a spectrogram of some sort of audio waveform. If you guys have ever played around with these, more or less what it does is it represents the relative frequencies of the image as hot and cold spots on this and stacks it over time with the frequencies of the y-axis. And you can use convolutional neural networks to do predictions on this. There's a lot of stuff for like specific types of medical classification as far as I'm aware. But generally speaking, a lot of the time audio is processed over time. So using something like an RNN or LSTM, which we'll be covering next week. Yeah, CNNs, super, super powerful, used everywhere. They're also used in conjunction with other networks. So talking quickly about in advance, something that is way out of scope for what we're covering in terms of RNNs, which are recurrent neural networks. We'll talk about this next week. CNNs can be used in conjunction with them. It's called a convolutional recurrent neural network, so or recurrent convolutional neural network, so RCNN, which more or less just allows you to take image data as a time series or vice versa. And it's real weird, but it's decently effective used in a number of places. You guys can look this up on your own. I don't actually know how it works very well because I don't ever really need to use it, but it's out there and it works. So that more or less is our examples of uses. And before we go on to the code, let's do a quick recap. Convolutional neural networks are designed specifically to run on images. They're used in other things occasionally because the technology is pretty useful. But they were originally designed specifically to run on images to solve the issue of neural networks not being able to process them effectively. The way it works is you pass filters over the images and extract patterns, and the patterns are condensed by pooling before being passed into a neural network after being trained. Is everyone feeling good about this stuff? Because this is basically how convolutional neural networks work. You don't need a lot of math for this. You just need to know like roughly what a convolution is, which we did on the board. It's literally that easy. All right, how are you feeling? Thumbs up, sideways down? Hell yes. Okay, cool. Before we go on the code, we wanted to give you guys a quick reminder for those of you interested in participating in the Skies Movement Workshop. These are weekly. We're doing it again. Woo! We love competitions. It's my favorite part of the year. Every part of the quarter that's a lie. It's not a specific thing that happens once a year. It happens every quarter. So workshops happen on Thursdays from 3 to 5 p.m. in E2 room 399. It's split into two halves. The first half is the catch-up. The second half is the main meeting, going on with the next steps, etc. And generally what's being planned to talk about this week, it seems, is type of model you should use and best resources to get started making one. And as usual, Ken will be helping people out with questions and blocks. He's been a huge help in running this, and without him, it really wouldn't be possible at this scale. So if you guys are interested in participating, I think the rules document has been sent in the Discord. If not, remind me and I'll send it. Because there are like one or two little changes that we made for this quarter. And in addition, it seems that this quarter there will be competition from other UCs. So before it was technically open for them, but because of very poor coordination, mostly on their part, that didn't really happen too much. So now we should have people competing from UC San Diego and UC Davis, if I remember correctly. So competition's bigger than ever. And you guys are free to work with anyone who's at another UC. They don't need to be involved with like clubs or with like their specific clubs, because I don't know if you guys know this, Berkeley, their ML club is tryout only, which is kind of rude and mean of them. There's tryout only. So if you guys want to work with someone at Berkeley who for some reason they turned out, feel free. Just need to be a member of the UC system. You're more or less able to. Competition should be fun. The theme, if you guys don't remember, is back to square one. So it should be a lot of fun. I encourage you to participate. It is a very, very good way to take what we're generally trying to teach you and put it into a little bit of practice, and also learn really data science techniques along the way. I highly encourage it. I'm very, very proud of the competition that we're in. So if you guys have time this quarter, it's one of the best things you can do is being a member. It's like seriously awesome. Yeah. Yeah. The workshops are weekly. I think we're trying to arrange some sort of Zoom thing, but don't quote me on that, because specifically because of the other schools and not wanting to offer them the same resources that we have. But yeah, generally it's just an E2. Okie doke. Any other questions about the competition? Yeah. Well, we're in E2 right now. So E2, this is just this building. 399 means it's on the third floor of room 99. So walk around there. Yeah. There's also a map right by the stairwell on both of them, or all three, I guess. And it's pretty obvious. So go to these. Kevin's a huge help. Really, really proud of the work that he's doing. And makes the competition look better. Oh yeah, and Cohen's also going to be there. There you go. More than help. Alrighty. I think that more or less covers this slide. So if anyone has any questions, feel free to come up and ask. Or shoot a message to myself or Cohen or Kevin or anyone with an orange name tag on the Discord server. Okay, cool. Last thing, it's code time. So if you want to do this and you have your laptop, QR code isn't really going to help you with this. It's there because I have inertia and I always put a new QR code in there, even though it's not really useful for us. So if you want to participate, go to tinyurl.com/sky-cnn-2024. We're going to show the cable news network what's up. All right. Yes, we post the slides and the recordings in somewhere. Yeah. Oh, you mean the slides themselves? Yeah, we post the slides themselves. Yeah, remember to make a copy, y'all. If you want your work to be saved, make a copy. But yeah, that'll more or less do it for us. Now, I am going to end the recording for other people on Zoom. Good time. Good luck with the code. Feel free to send me questions if you have them. Bye.